Title Nuclear Physics 1. The course code is 6 The topic is Yukawa Meson theory. In this whole topic, we will briefly discuss about what are the fundamental forces, what are the nuclear forces, classical concept about the forces, quantum concepts about the existence of nuclear forces, what is the Yukawa Meson theory, why it is necessary for the existence of nuclear forces, what is the importance of Yukawa Meson theory in the field of nuclear physics 1. This will be described briefly in this topic. Let us start our topic. The contents that we will discuss in the upcoming slides are four fundamental forces, nuclear force, Yukawa introduction, Yukawa Meson theory, types of mesons, nucleons interactions that involves pions, mesons. In this slide, we will discuss about the four fundamental forces of nature that are considered at the root of every interaction in the universe. These four fundamental forces act upon us every day, from playing basketball to launching a rocket into space to sticking a magnet on your refrigerator. All the forces of us that all of us experience every day can be whittled down to a critical quarter. We will discuss gravitational force, electromagnetic force, strong nuclear force, weak nuclear force. These are the basic four fundamental forces. Gravity is the attraction between two objects that have mass or energy. Isaac Newton was the first to propose the idea of the gravity. He described gravity as a literal attraction between two objects. You can say that gravity is probably the most familiar of the four fundamental forces. It is due to the gravitational force that we stay on the earth. Second force is the electromagnetic force. The electromagnetic force, also called the Lorentz force, acts between charged particles. Like as we know that there may be positive charge or negative charge. If the same charges we know that repel each other, but opposite charges attract one another. The greater the charge, the greater the electromagnetic force. As its name indicates, the electromagnetic force consists of two parts. The first one is the electric force and the second part is magnetic force. The electric components, you can say, acts between charged particles whether they are moving or stationary, creating a field by which the charge can influence each other. But once these charges set into the motion, those charged particles begins to display the second force, the magnetic force. So collectively this force is the electromagnetic force. The third one force that we are going to discuss is the strong nuclear force, that is also known as the strong nuclear interaction. It is the strongest of that are the basic building blocks of proton and neutron, the part of the nucleus, and part of the strong force also keeps the proton and neutron of atomic nucleus together. The fourth force is weak nuclear force. This force is also known as the weak nuclear interaction that is responsible for particle decay. You can imagine this is the literal change of one type of subatomic particle into another part. For example, a neutrino that stays close to a neutron can turn the neutron into proton while the neutrino becomes an electron. This is the example of the weak nuclear force. study what are the nuclear forces. As we know that nuclear force is one of the four fundamental forces of the nature. The nuclear force is basically the force that bonds the proton and neutrons together in the nucleus. As we know that in the nucleus of an atom, proton and neutrons lies. So where is the proton and the neutron? Obviously there are some nuclear forces that bonds together to stay inside the nucleus. These forces are basically the nuclear forces. These force can exist between protons and protons, neutrons and neutrons, or neutrons and protons. This is the basic nuclear force. Nuclear forces also known as nuclear interactions and strong forces. They are known as strong forces because, as we discussed in our previous slides, there are the four fundamental forces. Among all these four fundamental forces, our nuclear forces are the strongest forces that act between two or more nucleons. Here nucleons, as you know that the proton and neutrons that lies in the nucleus. These forces bind proton and neutrons into the atomic nuclei. The nuclear forces is about 10 times million stronger than the chemical binding that holds atoms together in the molecules. We can compare nuclear forces that bind the nucleons in the nucleus with the chemical binding forces that holds atoms together in the molecules. These forces are 10 times million stronger. In this slide, we will discuss the properties of nuclear force. This force is basically attractive in nature but with the repulsive force. That is the reason that the nucleus is held together without collapsing in itself. As we know that there are proton-proton interaction in the nucleus, as proton and neutrons are also present. This is because the nuclear force that nucleus is held together, although the repulsive forces are also present in the nucleus. The range of nuclear force is very short. As nuclear force we have already discussed is the strongest force among the four fundamental forces. As it is strongest force, but its range is very short. You can imagine at 1 Fermi, the distance between particles in a nucleus is very tiny. They are bound very closely to each other. Proton and neutrons that stay in the nucleus are tightly closed or packed. At this range, the nuclear force is much stronger than the repulsive Coulomb force that acts between the protons. As like charges repel each other, so there will be Coulomb repulsive forces between the same particles that are proton particles. So the nuclear force becomes heavier or stronger than the Coulomb repulsive forces. However, if the distance is more than 2.5 Fermi, nuclear force is practically non-existent. So it may be concluded that due to short range, nuclear force exists as a strong nuclear force. But with the increase in the range, like here we discussed at 2.5 Fermi, nuclear force is practically doesn't exist. This concludes that nuclear force is short range, strong force. We are discussing about the properties of the nuclear force, how it exists between the nucleons, what is the behavior of the nuclear force. The nuclear force is basically identical, or you can say same for all the nucleons. It doesn't matter if our nucleon is a proton or neutron. Nuclear force, due to the same force acts in the same way. It affects every nucleon or everything in the same way. The interesting fact about the nuclear force is that at a distance of less than 0.7 Fermi, this force becomes repulsive for the neutron. It is one of the most interesting properties of the nuclear force, as this repulsive component force is what decides the size of the nucleus. This repulsive nature of the nuclear force decides what is the size of the nucleus. In previous slides, we have discussed about the fundamental forces of the nature. What are the fundamental forces of the nature? What is the nuclear force? The nuclear force is most important force in the atom and molecular physics. When we discussed about the nucleons, we always discussed about the nuclear force, because basically this is the force that bonds the nucleus together in the atom. In this slide, we will discuss about the exchange force model. This model basically comes from the molecular and atomic physics. As we know that there is a chemical covalent bonding in chemistry. When two nuclei are bound together through covalent bonding, the valence electrons are just shared among both of the atoms. This is the chemical bonding. If all valence are filled, then it can't affect the presence of the third nuclei there. Similarly, if we discuss the nuclear exchange model, the incident particle changes its characteristic. For example, an incident proton changes into neutron, whilst the backward neutron changes into the proton. Thus, something is exchanged between the nucleons. It means that when proton changes into the neutron or vice versa, you can say proton change into neutron or neutron changes into the proton. Something is exchanged between nucleons, so their exchange becomes possible, and this something saturates this nuclear force. This is the basic of the exchange force model. Before going into the discussion of Yukawa Meson theory, we are trying to understand the things gradually. Now, in classically, it was thought that objects were interacted by means of action at a distance. The great development in theoretical physics in 19th century was the concepts of the field, for example, electromagnetic field and gravitational field. Students, in the early development of classical physics objects, it was imagined that one object mysteriously transmits through space its force on the other object. This is the action at a distance. Means to say that one object attracts or repels another object by a force. But as we discussed, in 19th century the great development was made. This is the concepts of the field. According to this, one object establishes the force on the other object through a force field. As electromagnetic and gravitational fields, the attractions occur with the help of the field. This turns the thought of action at a distance. The action at a distance possible only through the field force, that was electromagnetic and gravitational fields. The first objects interacts with the field, not directly with the first object. Their interaction possible through the fields. If there is one object and there is another second object, their interaction possible only through the field. It may be gravitational field or it may be electromagnetic field. This is the concept of the classical physics. As in previous slide, we discussed about the interaction of two objects classically. We have discussed that according to classical physics, interaction of two objects are possible through field. It may be gravitational field or may be electromagnetic field. But with the arrival of quantum mechanics, it was believed that all type of exchange energy must occur in some bundles of discrete particles. The classical theory is smooth and continuous, and to bring it in agreement with quantum mechanics only if the field of interaction between two objects must be quantized, means to say that it must emit energy in bundles of discrete particles. That is the concept of the quantum mechanics. According to quantum mechanics, the first object doesn't set up a classical field around the object through which it was attracting or repulsing, but instead emits field quanta. This second object can then absorb those field quanta and re-emit the back quanta to the first object. The two objects don't interact indirectly but directly with the help of exchange field quanta. This is the concept of quantum mechanics. Here we can compare two concepts, that is classical concept and quantum mechanical. According to classical effects, two objects interact through the field, but according to quantum mechanics, one object emits the quanta that is absorbed by the second object, and then second object release the quanta of energy back to first one. This is the basic difference between quantum mechanics and classical mechanics, that how one object interacts with second object. Students, as we are discussing about the interaction of two objects, how two objects interact quantum mechanically or classical mechanically. According to classical mechanics, as we discussed, one object emit the quanta discrete energy packets towards the second object that is observed by the second object. So whenever we study about the nucleon-nucleons interactions, the first thing is that how they interact. The answer is that thus through field quantas, as we discussed. So we can say that nucleon-nucleon interactions also obey the quantum concept. According to this concept, first nucleon emits something in the form of quanta that will be observed by the second nucleon. This is the basic concept of nucleon-nucleon interactions. Here is the diagram for proton-neutron interactions. As we discussed earlier, proton-neutrons are known as nucleons. In this diagram, you can see that they interact through the mesons. We will discuss briefly these types of mesons in the upcoming slides. A successful mechanism for the nucleon-nucleon force is that of the exchange force. Students, in this slide we will discuss about saturation of nuclear force. What is meant by saturation? Every nuclear exhibits a phenomena that is known as saturation. This can be defined as the volume of nuclei increases proportional to the number of nucleons. You can say that as the number of nucleons in the nucleus increases, the volume also increases proportionally. This property of the nucleon suggests that the nuclear force is of short range and strongly attractive at short range. As we discussed in our previous slides, that nuclear force is a strong short range force that explains nuclear binding. It is due to the strong nuclear force that proton-proton and neutron-neutron, that are known as nucleons, binds the nucleus of an atom together. The experimental support for saturation comes from the relatively constant nucleus density and binding energy per nucleon as we go towards the heavier nucleus. It must be understood that a given nucleon seems to attract only a small number of near neighbors, but it also repels at small distance to keep those neighbors from getting too close. In this way, our nucleus bonds the atoms together. As we go towards the heavier atoms, the number of nucleons are not equal. There may be large number of protons in the nucleus or large number of neutrons in the nucleus. As we discussed, our nuclear force is short range strong force. This or it also repulsive force at 0.7 Fermi. So this is due to the repulsive nature and of the nuclear force that for heavier atoms, when the number of nucleons are not equal, it acts here and our nucleus bonds together. As we discussing about the exchange model, a more successful explanation can be found or detected in exchange model if during the collisions the proton and neutron exchange take place. That is, if the forward moving neutron becomes a proton and the backward moving proton becomes a neutron in the center of the mass frame system. The incident nucleon that reappears in the laboratory as a forward moving nucleon consistent with the estimate of small angle in nucleon scattering. Now in this slide we will calculate mass of exchange particles. Before calculating the mass, we will discuss what are the exchange particles. It is natural to associate the something that is exchanged in the nucleon interaction with the quanta of nuclear field. When there is interaction of proton-neutron or proton-proton, neutron-neutron, there must be something exchanged during their interactions. For us, as we know that neutron has half spin. If neutron changes into the proton of half spin, it is clear that some particle is exchanged during their interactions. The exchange particle must have integral spin, not half spin. Its spin must be 0 or 1 and it must carry electric charge. In addition, if we wish to apply the sum exchange force concept to neutron-neutron and proton-proton interactions, there must also be an unchanged variety of exchange particles, because when their nucleon interactions happens, there must be something exchanged. When proton changes into the neutron or neutron changes into the proton, something is exchanged during these interactions. Now we will calculate what is the mass of the exchange particles. Based on the observed range of the nuclear force, we can calculate the mass of the exchange particle. If we know about the range of the nuclear force, we can easily calculate the mass of the exchange particle. It is not possible, you can say it is impossible for nucleon to emit a particle of mass energy mc square and still remains a nucleon without violating conservation of energy, unless the emission and reabsorption take place within a short time that we remain unaware about. Energy conservation law has been violated. It means that when the nucleon changes into the another nucleon, the conservation law violates due to the exchange of particle, but the reabsorption must be take place within a very short time to conserve the law of energy. Students, here we can say that we can calculate our energy by the Heisenberg uncertainty principle. As we know that delta I delta T is approximately equal to mc square, that is the value of E, into delta T, that is greater than h cut over 2. m particle of mass m and rest mass energy, that is E is equal to mc square, can be exchanged if it doesn't go outside the bounds of the uncertainty principle in the form. It means that when a nucleon changes into the another nucleon and exchange particle also emits, then the reabsorption also takes place in the short range to conserve the law of energy. Now we will discuss about the range of forces. A particle that can exist only with the constraints of the uncertainty principle is called a virtual particle. As we discussed in previous slide, while calculating the mass, we discussed that energy can be found by using uncertainty principle. And the time in the expression represents the maximum lifetime of the virtual exchange particle. The maximum range of the force can be determined by the maximum distance that the particle can travel in the time delta t. If the particle moves at the speed of the light, then the range can be written as R is approximately equal to C delta T. This formula is calculated by using formula S is equal to Vt. Here V is replaced by the speed of light C, as we are considering that particle is moving at the speed of light, that is approximately equal to h cut over 2 mc. It is experimentally observed that for nuclear forces whose range is 1 Fermi, it is clear that we must have an exchange particle with the mass energy of the order of 200 mega electron volt. As we discussed in previous slides, that according to quantum mechanics, one particle interacts with other particle through some forces. These forces are carried by the particles that are known as exchange particles. Actually, these particles are also known as virtual particles. We can define virtual particle as such particles that exist only for fleeting instants for short time and allows us to violate conservation of energy are known as virtual particles. These particles are not able to detect by human eye. We can observe the force that results from the exchange of virtual particles. Actually, when two particles or two objects interact with each other, quantum mechanically they exert force on each other. This force is carried by the virtual particles. We can calculate the magnitude of this force that is carried out by exchange particle, but we can't detect this particle by human eye because it is a virtual particle. It must be noted that exchange virtual particles can be identical or same with ordinary particles. That particle that we are very well known, the virtual particles can be identical or same with these particles. However, according to quantum field theory, the Coulomb interaction between electric charges can be regarded as the exchange of virtual photons, which have properties similar to the ordinary existing particles. As we discussed in previous slide, there is a diagram, that is Feynman diagram, in which we discussed a proton can be changed into the neutron or neutron can be changed into the proton through some particle. This particle was represented by the dotted lines. These dotted lines shows the virtual particle. So this was the basic concept of virtual particles. As we discussed in previous slides about the exchange of forces occurs through some particles. These particles are known as virtual particles. Yukawa, a Japanese physicist, was born in 27th of January 1903. In 1935, Yukawa proposed the existence of new kind of particle. These are actually the virtual particles. He called this particle the Meson's particle in order to explain how protons and neutrons in the nucleus interact. As we know that our nucleus in the atom consists of protons and neutrons, there may be the interaction between proton and proton, neutron and neutron, or maybe between protons and neutrons. So Yukawa basically explained the types of the interaction that are involving inside the nucleus. The proton, as we all know that discovered in 1999, and neutron in 1932. Yukawa basically contributed his efforts to describe the interactions involving the nucleons in the nucleus. Yukawa Meson theory basically gives an idea about the nuclear X force between two neighboring nucleons. There is a force that acts between nucleons due to exchange of subatomic particles called as mesons. Basically, as we discussed in our slides, that when two particles, two objects, or maybe two nucleons interact with each other, they exert force on each other. But this exchange of force takes place through some virtual particles. These virtual particles are known as mesons, as described by Yukawa. Mesons are the parts of atomic particle which may be charged or uncharged. There are different types of the meson that we will study in upcoming slides. Mesons basically carry charge or may chargeless. The exchange particles that carry the nuclear force during the interaction of the nucleons are known as mesons. Basically, meson's word comes from the Greek language meso, meaning middle, because the predicted mass was between the masses of the electron and the nucleon. As we are discussing that mesons carry the exchange force during the interaction of the nucleons or particles. So mesons mean meso, the middle. Its mass lies between the masses of the electron and the nucleon. This is the basic concept of the meson. As we are discussing about the virtual particles that carries the exchange force while the interaction between the nucleon particles or the objects according to quantum field theory. As Yukawa introduced the theory, introduced the concept of the mesons. Basically, there are three types of the mesons that are categorized upon the charge carried by these mesons. Number one is neutral pi mesons. Then second type is positive pi meson. Then negative pi meson. Actually, neutral pi mesons are known as neutral because they carry no charge. No positive, no negative charge is present on neutral pi mesons. So, as they carry no charge, they are known as neutral pi meson. Positive pi meson, as name show that they carry positive charge. Their charge is equal to positive 1 plus 1. When we discuss a negative pi meson, as their name shows that negative, it means that it carry negative charge that is equal to -1. This is about the charges of the meson charges that is carried by these mesons. When we discuss about the spin of this meson, all three types of the meson, neutral pi meson, positive pi meson and negative pi meson, carry zero spin. And there, if we discuss about the rest energies of the mesons for positive pi meson and negative pi meson, the calculated value is 139.6 mega electron volt for the energy, and the calculated value of energy for neutral pi meson is 135.0 mega electron volt. All these values are calculated. Now we will discuss about the behavior of these mesons for different ranges. At shorter range, that lies between 0.5 to 1 Fermi, exchange of the mesons is probably responsible for the major nuclear binding when the range is short. At much shorter, when we go approximately 0.25 Fermi, exchange of mesons for energy equal to 783 mega electron volt may contribute to the repulsive force. As we discussed in previous slides, that for shorter range the forces becomes repulsive for nucleon, and there are also Coulomb repulsive forces between proton nucleon in the nucleus. Whereas if we discuss about the exchange of mesons for energy 769 mega electron volt, it may provide the spin orbit part of the interactions. This is the basic introduction about the types of mesons and how at different ranges these mesons contribute in different types of the interactions. According to the Meson theory or Yukawa theory, all the nucleons that are present inside the nucleus of an atom are made up of an identical cores that are surrounded by a pulsating cloud of pi mesons. It means that, as we see in low diagram, there are neutron and proton. Neutrons and protons are present inside the nucleus and they are known as nucleons. Their interactions is done by some virtual particles that are, according to the Yukawa theory, these particles are mesons. So there exist a meson clouds around these nucleons. The main purpose of meson cloud is such that when neutron changes into proton and proton changes into the neutron, there is the interaction of the mesons. Meson may be absorbed by a particle or meson may be released by a nucleon. This is basically meson cloud that makes sure the interaction of neutron and proton in different ways. Basically, it is the Yukawa's attempt to find a core or a potential that would describe the exchange of particles that gives rise to the nuclear forces due to the interactions. In much the same way that the electromagnetic potential and fields describe the exchange of photons that give rise to the electromagnetic force due to the interactions. One major difference between the electromagnetic interactions and strong nuclear interaction is that electromagnetic force exists for infinite range, while the range of the nuclear force is 1 Fermi. As we discussed that nucleon exists in the nucleus. So there are different types of the interactions that gives rise to the nuclear force. When these reactions that involves the nucleon takes place, the nuclear force exists. The existence of nuclear force occurs through the exchange particles. Yukawa called these particles as mesons, that is described through Yukawa meson theory. These are things were discussed briefly in previous slides. As we discussed, there are three types of the mesons: neutral pi mesons, positive pi mesons, and negative pi mesons. So we can say that a meson may be pi plus 1, pi 0, or pi negative according to the charge present on the meson. As we discussed, whenever a neutron accept or eject a meson, it may changes into the proton. Similarly, a proton may accept or may eject a meson, and in turn it changes into the neutron. So it was observed that if a neutron accepts a neutron, as we discussing, by accepting a pi plus meson, it converts into a proton. When there is the interaction of neutron with pi plus meson, it will changes into the proton. Similarly, if a proton accept a pi minus meson, it will be converted into a proton. If proton eject pi plus meson, it will again converted into the neutron. In the same way, if neutron eject pi minus meson, then it converts into a proton. This is the basic view how a neutron can be changed into the proton by accepting a pi plus meson. Similarly, proton changes into the neutron by when it interacts or there is a bombardment of pi minus meson on the neutron. If we eject the pi plus meson from a proton, it again changes into the neutron. Similarly, if pi minus meson is ejected from the neutron, it changes into the proton. This is the basic view how proton neutron changes into one neutron to the other neutron through the exchange of mesons or virtual particles. When these interactions occur, there is the release of the nuclear forces. As we discussed in previous slides, that the nucleons, one nucleon may be neutron or proton, changes into the second one nucleon through the exchange of the mesons. In these interactions, mesons may be absorbed by a nucleon or may be ejected by other nucleon. You can see from the reactions, proton when accept pi minus meson, or there is the interaction of proton with the pi minus meson, it changes into the neutron. Similarly, if neutron accept a pi plus meson, it changes into the proton. This is the basic view how the proton or neutron interactions occurs in the nucleus. Basically, it is due to these virtual exchange particles that binds the nucleus together that are responsible for the exchange of the forces according to quantum field theory. When these nucleons interact with each other, there is the exchange of some particles through which these forces are ejected. Now we will discuss about what is meant by OPEP. This is the basically abbreviation of one pion exchange potential. In particle, atomic and condensed matter physics, Yukawa potential, that is also known as OPEP. It is also known as Coulomb potential, is a potential named after the Japanese physicist Yukawa that basically give the idea of mesons, also known as Yukawa meson theory. This equation is in the form of U is equal to G square E minus lambda R over R, where lambda is a constant, that correspond to the inverse of the range of nuclear forces. R is the distance between nucleons that are interacting with each other, and G is the magnitude of the nuclear coupling constant. It has the dimensions of the charge. The potential is monotonically increasing in R, and it is negative, implying that force is attractive. In SI system, the unit of Yukawa potential is 1 per meter. The Coulomb potential of electromagnetism is an example of Yukawa potential with the value of e raised to power minus lambda r equal to 1 everywhere. Basically, in this equation, G squared gives the strength of the interactions. How is the strong our interaction? This is determined by G square. So as far we have discussed about exchange force model, the exchange force model enjoyed a remarkable importance in calculating the properties of nucleon-nucleon system. Where there are nucleon-nucleon system, the exchange force model plays an important role as it determines the strength, the range of the interactions. The forces are based on the exchange of virtual mesons as described by the Yukawa theory, all of the which can be produced in the laboratory and studied directly. So this is the basic introduction of one-point exchange potential, abbreviated as OPEP, that determines the interactions between, just as Coulomb interactions between the nucleons. As we discussed, according to quantum field theory, a field always has a combined particle that is necessary for the interaction of two particles, and Yukawa introduced the charge-heavy quantum that mediated such nuclear forces. Yukawa introduced the concept of the mesons. We have discussed that the existence of virtual photons seem to violate the law of conservation of energy. But as we say that it is necessary for the exchange particles to obey the uncertainty principle. As they obey the uncertainty principle, and these particles exist for very short lifetime, the photon's excess energy is less than the uncertainty in its energy. The virtual photon can exist for very short time intervals, such as delta E approximately equal to 2 over delta T. Their energy is very high, but their existence is for very short time in order to obey the law of conservation of energy. Relationship between the mass of the particle and the range of force was given by the formula lambda is equal to h over mc. From the known approximate range of the NP interactions, Yukawa showed that the mass was about 200 electron masses. It means that their masses are so high. According to Yukawa's concept that a system of the two nucleons that can change into the other nucleons plus a mesons as long as it returns to its original state in a very short time interval. It is often said that nucleons undergo fluctuations as it emits and absorbs fields particles. This is the concept that was given by the Yukawa. So this was the great work that was contributed by the Yukawa to introduce the existence or to describe the existence of the nuclear forces that occurs by the exchange of the particles. And so in conclusion, we can say that mesons are actually the virtual particles that exist for very short time of interval and carry large energy. Thank you so much. This is the student. This is all about Yukawa Meson theory. Hopefully you understand all the topics. Thank you so much.
ਸਾਡੇ ਨਾ ਖਾਨਦਾਨ ਚ ਵੀ ਅਕੀਦੇ ਦੀ ਬਹੁਤ ਕਮਜ਼ੋਰੀ ਆ ਨਹੀਂ ਬਾਕੀ ਫਰਜ਼ ਜਿਹੜੇ ਆ ਨਾ ਫਰਜ਼ ਸੁਣਤਾ ਵਕਤ ਨਫਲ ਵਗੈਰਾ ਉਹ ਫੇਰ ਵੀ ਘਾਟਾ ਵੱਧਾ ਉਹਦੇ ਕੋਲ ਜਿਹੜੀ ਗੁੰਜਾਇਸ਼ ਹੈ ਅਕੀਦੇ ਦੀ ਗੁੰਜਾਇਸ਼ ਨਹੀਂ ਹੈਗੀ ਅਕੀਦਾ ਤੋਂ ਹੀ ਜਿਹੜਾ